having me here. It's my great pleasure and honor to just talk a little bit about data and computation in some of our recent works related to federated learning. So if you look at key challenges in AI these days, like one of them I would say is imbalanced data availability across different populations, and there's also some recent studies showing that there's insufficient public data. So obviously federated learning is a way to unlock private data for model training, so that is quite useful. And the other challenge is we may have imbalanced access to computation resources, which means if you consider federated learning clients, maybe some clients may participate much more often than others. And there's also an energy aspect, like for example, some big companies can look into nuclear energy, but some smaller companies or personal users cannot do that. So in the following, I'll be talking about some of the recent things we did related to those challenges. So one is, so once you have a trained or a machine learning task, you need to have data, right? And in many cases, data come from different sources, and we need to improve the data quality because some data may not be very useful for model training. And then once you have the good data, we may have them located in different clients, and the clients would participate in the federated learning process, but when they participate not equally, we would not like to have the model to be biased towards certain clients' data, so we want to debias the contributions. And so then we will look at what happens if we are really looking into a large language model training, where it's probably hard to track where the data comes from, or in some data center environment, you probably don't have the notion of clients either. So we also have a loss reweighting approach to do the debiasing. And then in the end, I will be also talking a little bit about some future directions. So let's start with how to select high quality data. So this is some challenge that we did or we resolved at IBM because we wanted to train large language models, and the data comes from different sources. And the challenge is that sometimes you have a lot of duplication, and some data samples may not be good, and sometimes it may include bad language and so on. So what we did is to develop this data prep kit with an open source repository. The link is shown here. So the data prep kit can clean up the data so that it's very useful for model training after the cleaning. The result that we get is this GrindNet 3.0, or actually we have 3.1 and probably 3.2 as well these days. So this is a model that we trained. We outperform the benchmark models that are also open and have the same number of parameters as our model. And we recently also opened this nice web, basically that is a recipe for data processing for large language model training. So now let's say we have a good data, then we want to train the model in a federated setting where the data is distributed. So just a quick review of what's the objective of federated learning. As you probably all know, so we usually have a client, a local objective at each client, and we also have a global objective. We don't observe the global objective directly because the local objectives are defined related to the local data, but we want to minimize the global objective. So a solution is the federated averaging algorithm, which includes local updates and aggregation. But something we consider here is that, so in many practical cases, you may have different client participation frequencies depending on their computation capability and also whether they are connected to the power and those kind of things. And also to resolve some of those like imbalanced participation, we can introduce aggregation weights that I will be explaining in the next slide. But just with the notion of aggregation weights, so let's see what federated averaging or the original federated averaging algorithm does with aggregation weights. So basically, in the original federated averaging algorithm, you have an aggregation weight of 1 for all the clients, and that means if we don't do anything, then using the original federated averaging algorithm, we will be optimizing reweighted objective compared to the original objective. So if you want to optimize the original objective instead, what we can do is to estimate the aggregation weights. And this is based on the paper that's shown here. So the idea is also kind of obvious maybe, so because in the previous expression we have the objective being weighted by the product of the aggregation weight omega n and also the participation probability Pn. So if we know Pn, then we can choose omega n to be 1 over Pn. But in practice, we don't always know how often the client would participate beforehand, and in that case, we can estimate the participation probability. But there are some practical challenges in this estimation, so I probably won't go into all the details, but the main idea is that if we just do a regular estimation, sometimes we may have large intervals and that can cause an overestimation. So what we introduce in this work is a cutoff interval that can control the balance between the bias and variance of this aggregation weight estimation process. Now, in terms of convergence guarantees, we also show that we have a weight error term in the result, and for the final result, there are some terms that are standard in the fed-width averaging algorithm, and there are there's a new term that's related to this optimization or estimation procedure of aggregation weights as well. So looking at the experiments, we compare this FedAU algorithm with some baselines where you average the participating clients or other clients. So we outperform those. And also if we choose the cutoff interval k equals to 50, we perform better than the case of k going to infinity, which is the case where you don't have the cutoff interval. So now let's then look at what can we do if there's no information about client. So in the case of large language model training, maybe you have a lot of clients participating. You may not be able to track all the clients, or maybe they are participating only once or twice during the whole process. So in this case, we developed this re-weighting method based on the losses, because if the loss is big, then we can say that the model already or the model doesn't know this sample very well. So in that case, we can put a higher weight. But on the other hand, if the loss is small, we can say that the model probably already knows about the sample quite well already. So, and we also see some performance improvements with this approach and pre-training a 7 billion parameter model. So then what comes next? So one thing I would like to share here is some thoughts about privacy, because looking at the computational aspect of federated learning, so I would say that computation can be, it's a very useful aspect in federated learning if you have cross-silo applications in particular, because they may not want to send everything to the cloud. And in those cases, maybe some best effort privacy preservation would be acceptable. So we should also welcome any different types of privacy compared to some traditional ways of privacy definitions like secure aggregation and differential privacy. So the next thing is, I think AI agents is really something that is very popular these days. So we are organizing a workshop on federated agentic workflow. So we welcome everyone to submit to this workshop, and this QR code is the link to the workshop webpage. So that's all. Thank you very much.
Into data prep kit, somehow an index to measure the quality of the data to know how good the data is indeed.
Yeah, that's a very good point. So currently we use some lightweight models, like some linear classifiers, like FastText models, for example, to score different data samples. And based on the scores, we say whether this sample should be kept or not. There could be other ways to do that, but usually we try to do it in a lightweight method, in a lightweight manner, because the data volume could be huge. If you have a smaller amount of data, you can apply probably some model-based or some more complicated model-based approaches as well.